Hi, everybody. I'm going to do an abbreviated lesson to finish out the unusual or the polar curves. As you look at this one, 16 sine 2x is like a sine-looking curve. But what do you think happens when you throw a square root around it? In the chat, take a minute. What do you think the difference is? What happens when you put a square root around a sine curve like that? Any thoughts about that? So I see an idea about like the shape of the curve itself. Is it more jagged? Is it smoother? Is it compressed? Talia, when you say compressed, do you mean in like a horizontal way or a vertical way? And Jonah says it can't be negative. What can't be negative? Okay, so two things. It does become horizontally compressed, but Jonah said something about negatives. I don't I don't know the what TBH means. I don't know. I know what LOL means, but I don't know what TBH means. Oh, to be honest, okay. And then I see Yusuf says it can't. Yes, it disappears. So let's take a look here on my screen. In red, I have 16 sine 2x, and then in green, I have square root of 16 sine 2x. It kind of like does a horizontal compression, but it also disappears. So what that means is when I change this thing into when I graph it in polar, whether I call it r squared equals 16 sine 2 theta, or if I take the square root of both sides, r equals square root of 16 minus 2 theta. Either way, we end up with a figure 8 looking thing, that green thing, not the red one. The red is if it was just 16 sine 2 theta, r equals 16 sine 2 theta. But the green, two petals of the rose curve, that figure 8 looking thing, it is called well, I know how to spell it, Leminscate. I always called it a lemon skate, but Mr. Stir calls it a Leminskit. He's probably right. But there it is. That's the figure 8 thing. So that's a curve I wanted to show you about. Now, the last topic in this unit is to look at like unusual curves and how we might be able to find the equation of them. And I'm going to show you a hold on. I need to switch the window. Let's see if I can do that. Okay. Hold on, everyone. Okay, I stop presenting and I go back to presenting a Chrome tab. Here we go. Okay, so now what you should see on the screen is an unusual curve, and it's called concoit. And actually, often it has this thing on the bottom also. These two branches. Wait, let me get my. Hold on, is it there? Yes. I think I need to move this. Okay, maybe you can see more of it now. So what a concoid is, this strange curve. Watch what happens when I move this point F around. It shows you how the concoid, the property of the concoid. What stays the same is from F to G is always the same length as line segment CD. So let me just kind of move it around. You can see that. Let me switch back to the iPad. I think I can explain this better by just drawing it by hand. Hold on. Things are a little complicated here with if you knew the number of windows that I had going on at the same time. Stop presenting. And now presenting a window. Here we go. Okay, you should see on the screen the iPad again. Here we go. Okay, let me tell you a little bit about the concoid of Nicomedes. Basically, what you have is a line, which is actually called the directrix, and you have a point, which is called the pole. Then you have this other random line segment, which is known as the distance. And the way you get points on the concoid is you pick a point, any point on the directrix, and you go from the pole towards the directrix. And then, here's the tricky part, you continue the line so that the continuation is the same length as this distance thing. So if I pick a different point on the directrix and I go towards it, as soon as I hit the directrix, I continue this amount so that this point will actually be a little bit higher up than this point because it's at sort of because this angle is different. If I go straight up, for instance, this will be at the highest point. It's always equal to this distance. And if you do that all around, you end up with a curve that looks a little bit like a bell curve, and it's got a an asymptote. Oh wait, there's a comment there. Now, the loop on the bottom, let me use a different color for that. So if I instead go to this point, just like before, but instead of continuing it in this direction, instead I turn around and go backwards. And someone asked, yes, the distance is past the directrix. Now, if instead of going past the directrix, I turn around and go backwards in this direction, this distance, I end up, so if I go over here and I go here and then I go backwards, whatever the distance is, that's when I end up with this, I end up with a loop that ends up happening on these things where you get like this loop. And that curve, it depends on, you can get different shaped concoids of Nicomedes. Let me see how quickly I'm able to sort of switch, stop presenting, present now, a window, no, present now, a Chrome tab, concoid of Nicomedes. So now you can look at this a little better. You can see this happening, but look what happens if I change the distance, my concoid changes also. And that also goes if I change the pole. Actually, if I make it too low, I don't get a loop-de-loop on the bottom anymore. And if I make it really close to the center, it ends up looking almost like a circle. And if I go above, the loop-de-loop goes on the bottom. Without getting too much into it, the Concoit of Nicomedes is a fairly famous curve. Let me go back to a window. There it is. Concoit of Nicomedes is like a famous curve. Isaac Newton thought that it should be like up there with like ellipse, parabola, and hyperbola, that it was that important. The history behind that name is that concoid is Greek for like shellfish. I guess it looks a little bit, or like the seafood mussel. Anyway, Zachary asked a good question, and that's where we're going with this. Does this thing have an equation? And the answer is yes, it does. But it's a difficult equation to figure out, but it actually is very much suited towards polar coordinates. So I'm going to take you through how you might find the equation. If you see on the screen, you see a concoid. And if I call this random point on the concoid r theta, where r is this distance, and I'm going to make the pole itself is going to be also the pole of the polar graph paper. So there's theta there. Now, in this question, they're telling you, hold on, 1, 2. We can see that the magic number, the length of the distance here, is going to be 4. The reason I know that, and I'll use a different color for this, if from the pole I go straight up, I go to the directrix there is at y equals 2. And then to get to this peak here, I would have to go 1, 2, 1, 2, 3, 4 more. That's why 4 is definitely the magic number, or the distance for this concoid of Nicomedes. So what can you say about this green line segment that I just drew then? Someone could type that in. How long is that green line segment? And I see Melissa and Talia wrote 4. And that's right, because that's what makes it a concoid. No matter which direction I go, if I hit the directrix and I continue, this line will equal whatever this is. So that's also 4. Now, see this little right triangle here? I'm going to sort of inflate that a bit. This is theta. Anyone know what you can say about the hypotenuse? Of course, the hypotenuse depends upon theta, but yes, Jessica says r minus 4, which is right. R is the entire distance from the pole to this point. And if this piece is 4, that's r minus 4. Now, this side here is just 2. It's given, basically. It's given that the y equals 2 is the directrix. So the equation that relates these two things is sine theta equals 2 over r minus 4. Cross multiply r sine theta minus 4 sine theta equals 2. And then if you add 4 sine theta to both sides, you get r equals 4 sine theta plus 2. R sine theta, sorry. Then if you divide both sides by sine theta, you end up with 4 plus 2 over sine theta. All right, 2. Is it over 2 sine? I think it's 2 over, I got a little confused. Sorry about that. R sine theta equals 4 sine theta plus 2. Divide both sides by sine theta and get 2 over sine theta plus 4. Which, if you want, you could write as 2 cosecant theta plus 4. And if you want to be convinced that that's true, let me bring up Desmos. And let me switch over. Hold on. Stop presenting. Start presenting. Window. Nope, not a window. A Chrome tab. Getting better at this. So if I type this in, R equals 2 equals R equals 2 over sine theta plus 4. Check it out. That's the equation of that concoid. So there's an example of a famous curve. If you're interested in the concoid, oh, you could have also said cosecant. If you have interest in the concoid of Nicomedes, it was used to trisect the angle long ago. One of the three famous problems of antiquity in ancient Greek math. So that's the concoid of Nicomedes. Now, I have as a challenge a couple of other curves. Let me come back over here. Let's see. Stop presenting. Present a window. And back to here. So I have two pretty challenging questions that you'll do as like a homework assignment due, in a couple of days. I want to explain them to you, and you can work with, friends on it. So here's a curve that's called the Kappa curve. It is the red curve in the picture that you're looking at. Let me explain the properties of the Kappa curve. So the way the Kappa curve works is you have a line and a point, which is point C. And let's see if I have this right. Hold on a second. I got it. It's been a while. You pick a point on this line, call that point B. You connect point C to point B. Oh, and there's also this point A, which is always just perpendicular right above point C. So the given thing is this line, point A and point C. Then you pick a random point, which is point B. And here's the kind of weird part. You then take the length of AB, whatever it happens to be, and you transfer it over here so that C is one of the endpoints. And the other endpoint is called point D. And D is the point on the Kappa curve. So just to show you another example, up here you can see that I have the B point here, and AB is this length. And if I go from C and go towards point B, but I go just as long as, so that CD is the same length as AB. So here's like another example. If I come all the way over here and I draw this line, and then I take this big green length here, and I transfer it over here, and wherever this point ends up is the point on the Kappa curve. And that creates this sort of bird-shaped thing. So the question is, what is the equation of the Kappa curve? And it's a pretty hard question. Let me erase all this. The trick to the Kappa curve is, let's call C is going to be the pole, and point D is going to be R comma theta. So R is this length right here. Now theta is this angle over here. Now the issue is I don't have I'd like to create a triangle that has R and has theta in it. And this is a very hard question. The trick to this question is that the triangle is not where you would expect, but the triangle is actually this upside down triangle, because that triangle also has theta in it. Oh, I forgot to tell you something important about this. Let's just say that AC is 10 in this case. Like I'm giving you that this point A is a certain distance away. So let's just say that that's 10. So this looks interesting. I got the theta, I got the 10. I have the R at least kind of in the triangle, but not really, because R is just this piece. R is just from here to here. Anyone know what the sneaky trick is because we have theta, we have an R kind of in there, but not really, because we know nothing about this other piece, this CB. Yes, AB is also R. That's the trick to this question. That's the definition of the Kappa curve, that this distance here has to equal that. So if this is R, that's also R. So my triangle looks like that, and that's why the answer is tan theta equals opposite over adjacent, 10 over R, or R equals 10 over tan theta, sorry. I'll put this one up on the screen in a second, but let me show you what the challenge problem is for you to do for part of your homework. This last curve is also a famous curve. It's called the cissoid of Diocles. Oh, someone has to go back. Here's this. So Jonah, you can see that that blue triangle, or the green, what I made is the green triangle. Theta is in the top right here. R is the adjacent side, and 10 is the opposite. I forgot to tell you in the beginning that A to B was length 10. You have to be told that. Actually, I'd like to show you the Kappa curve on Desmos before I put up the challenge question. You are presenting, stop presenting, present now. A Chrome tab. Yesterday, I didn't know. Was my face on the screen yesterday? Did anyone notice that? See, I didn't know that for the whole time.
Yeah, it was.
It was, yeah. I didn't know that until I watched the video. If you know you're being filmed, you might. I hope I didn't make any like exasperated faces or anything like that. But I edited myself out. That took a while to do. Now I'm covering up my screen. Not that I just don't look. Like it takes me a long time to get ready in the morning. Let's look at Desmos graphing calculator. So for this one, it's R equals 10 over tan theta. Oh, interesting. So you see over here, it's that's the bird thing, but I guess somehow this bottom part, but this top part is what I was getting at there. Okay, so now let's get to the challenge question.
Why is like the rotation of the sine stuff cosine, but the rotation of the tan stuff is cotan?
So, well, sine, cosine is a shifted sine curve, like sine plus 90, sine of theta minus 90 or something like that. Whereas tan is cotan shifted. So it's because, how a shift kind of becomes a rotation in polar. So that's why that happens. Okay, so now let me get the challenge question now. Stop presenting. I mean, you guys saw me yesterday. I wasn't looking like, so bad, but I just didn't know I was on screen. That's all I'm saying. If I know I'm on screen, I might, put some mousse in my hair. Do they still make that? Mousse. Here, present gel, present let me get the last thing for today. A window, movie recording. Okay, so here's the challenge question now. And this is one that you can do and talk to people about and do for homework. This one's pretty hard, actually. The last one is called the cissoid of Diocles. And you can see it looks like a sideways Kappa curve, but it has a much more complicated equation to it. Let me explain how the cissoid of Diocles is defined. Okay, so the way it's defined is you have a circle, and you have this line sort of tangent to the perpendicular to the diameter there. And the way this one works, you have point A here, is on one end of the diameter. You pick a random point on the line, and you join A to D. And then, get this, where it intersects the circle, you call that C. And then you take this length, this CD length, and you transfer it over there, and the endpoint of it is point P, which becomes, when I do that for a bunch of other points, becomes the curve. So it has a very similar definition, but it actually has a much more complicated equation. And I'll have you mess around with this as a homework question. It's a really hard question, and I encourage you to AB is perpendicular to BD, someone asked. If you pick a point that's far enough away, then this length here becomes kind of long. So then when you go to A and transfer that length, it actually ends up over there. So that's kind of confusing. You could have, like, if CD is too long, it can cross over with AP. Like this P point here could end up on line CD if it's long enough. So that's a little bit confusing. But once again, you're going to call the point that's on the curve R theta. And this will be R, and that will be theta. And it's up to you to try to find some right triangle that somehow has R and theta in it. Oh, and let's call AB 10, just if we do need to know what the diameter of the circle is. That curve is also famous. These curves, these crazy curves, cissoid of Diocles, concoit of Nicomedes, they were all invented in ancient Greece as cheating ways to do impossible constructions, like trisecting an angle. You can't do it with a compass and a straight edge. So they invented these unusual curves in order to accomplish the three impossible constructions. Okay, so that's today's lesson. Let me stop my video, but then I'll say a little bit more just to the class. Let's see. Hold on a second. Here we go. Stop recording.